This is a video for Newton's second law for rotational motion about a fixed axis. First we have to understand what rotational inertia is, or also it's called moment of inertia. It gives us a value it gives us a value to know how difficult it is to start or stop an object from spinning or rotating. It's analogous to mass with linear equations. So rotational inertia in the rotational equations is like mass in the linear equations. Here are some rotational inertia values for some objects. Now, in linear sense, we would say that mass is measured in kilograms, but here these different objects have different difficulties of spinning. If you have a thin-walled cylinder hoop, the rotational inertia I is equal to mr squared, which is the mass of the hoop times the radius of the hoop squared. And if you look through these charts, you'll see different rotational inertias for different objects. The larger the rotational inertia is, the more difficult it is to spin that particular object. There's an equation that goes with this, and it's very similar to F equals ma, force equals mass times acceleration, but instead of force we have torque, instead of mass we have moment of inertia, and instead of acceleration we have angular acceleration. The equation looks like this: the sum of the torques equals I alpha. Instead of the sum of the forces equals ma. This is sum of the torques equals I alpha. In this equation, alpha, the angular acceleration, must be expressed in radians per second squared. Here's an example problem. You can pause the video, see if you can try to solve it. It says here the motor in an electric saw brings the circular blade from rest up to a rated angular velocity of 80 revolutions per second in 240 revolutions. One type of blade has a moment of inertia of 1.41 times 10 to the negative second kilogram meter squared. What net torque, assumed to be constant, must the motor apply to the blade? Now we're going to use torque equals I alpha instead of R cross F, or instead of torque equals force times lever arm distance. We are now going to use I alpha. But in order to solve for this, we have the I value right up here, but we have to find alpha. So we'll go ahead and use one of the kinematic equations, omega squared equals omega naught squared plus 2 alpha theta. We'll use this information to solve for alpha, plug in our values, and we come up with our alpha value. And then we go ahead and use sum of the torques equals I alpha. And you'll see when we plug all those values in, we end up with an answer of 0.118 Newton meters for our torque. Another section of the textbook talks about rotational work and energy. And the definition of rotational work is that rotational work is done by a constant torque in turning an object through an angle theta, has the equation work equals torque times theta. Instead of work equals force times distance, we have work equals torque times angular displacement. Theta must be in radians, and work ends up being measured in joules. The definition of rotational kinetic energy is this. Instead of kinetic energy equals 1/2 mv squared, it's kinetic energy equals 1/2 I omega squared. So the kinetic energy of an object that's rotating is, instead of 1/2 mv squared, it's 1/2 I omega squared. Omega is in radians per second, and kinetic energy ends up being in joules. Now the idea of that the net work equals the change in kinetic energy holds true for these cases as well. The next idea, since we're talking about energy, the next idea we'd like to discuss is the idea of conservation of energy when you include rotational energy. So if you look at this box here, you'll see total mechanical energy is made up of 1/2 mv squared, and there's also plus the mgh, but you also now have 1/2 I omega squared. You have the rotational kinetic energy also. So the total mechanical energy at one position equals the total mechanical energy at another position, and if that object is rotating, you have to take that into account, the rotation of the object. Here's an example of a situation where these objects actually end up at the bottom of the ramp at a different time. If this ramp was frictionless and you let this solid cylinder and this hollow cylinder slide down the frictionless ramp, they would actually both reach at the bottom at the same time. But I want to know if they start from the same height, if you let them roll down the hill, which one gets to the bottom first. And you'll see that the solid cylinder gets to the bottom first because the hollow cylinder has a larger rotational inertia, therefore it's more difficult to rotate, therefore it takes a longer time to get to the bottom. Now the total energy is the same everywhere you go along this path, but it just so happens that this solid cylinder has a larger translational kinetic energy, linear kinetic energy at the bottom than the hollow cylinder does, because of that rotational kinetic energy is larger for the hollow cylinder than it is for the solid cylinder. If you look at the equation to explain this, on the left-hand side, you'll see the total energy final, and on the right-hand side, you'll see total energy initial equals each other. It's the kinetic energy, translational kinetic energy, then you have the rotational kinetic energy, and you have mgh. Now, in certain situations, you'll have zero. Like, for example, the final position has a height of 0, and the initial velocities are 0, so those would be 0 there as well. So then you end up with this equation here. And you'll see that if you solve for the final velocity of a hollow cylinder, it's a square root of gh. And if you solve it for a solid cylinder, it'd be the square root of 4/3 gh. The last thing we're going to talk about is angular momentum. Now, we learned about linear momentum, but now we're going to look at angular momentum. In Chapter 7, the linear momentum p of an object is defined as the product of its mass m and linear velocity v. So p equals m times v. For rotational motion, the analogous concept is called angular momentum, and it has the variable L. The mathematical formula of angular momentum is analogous to that of linear momentum, with the mass m and the linear velocity v being replaced with the rotational counterparts, the moment of inertia I and the angular velocity omega. So the definition of angular momentum, the angular momentum L of a body rotating about a fixed axis is the product of the body's moment of inertia I and its angular velocity omega with respect to that axis. So here's our equation. L equals I omega. Angular momentum equals rotational inertia times omega. Omega must be in radians per second, and angular momentum, the units for that are kilograms meters squared per second. So since there was the conservation of linear momentum, we also have something called the conservation of angular momentum, which states that the total angular momentum of a system remains constant if the net average external torque acting on the system is 0. And then we learned about it, external torque and internal torque. So we don't want any external forces causing the object to accelerate. So here's an example. An ice skater has her arms stretched out, and what happens is she has a certain rotational inertia here, and she pulls her arms inwards, her rotational inertia actually changes. It's easier for her to spin, that I value becomes less, so she actually spins faster. That's an example of conservation of angular momentum. The angular momentum before equals the angular momentum after. So you can pause this video and read this explanation that talks about the rotational inertia of the skater has decreased, so the angular velocity increases. This also holds true, this example holds true for a satellite going around the Earth. You'll see there's an apogee and a perigee, and what happens is the angular momentum out here at the apogee is equal to angular momentum out there at the perigee. It's very similar to when the ice skater pulls in her arms. We have the satellite, when it's closer to the Earth, has a smaller rotational inertia, so it has a faster angular velocity. Now you have these different givens here that are shown, but what we really know is a satellite moving in an elliptical orbit about the Earth, the gravitational force exerts no torque on the satellite, so the angular momentum of the satellite is conserved. Now to look at that mathematically, what we say here is that I omega equals I omega. In other words, the angular momentum before equals the angular momentum after. In other words, angular momentum out at position A equals their angular momentum at position P. Now, the I value for a mass going around the Earth is this mr squared. Angular velocity has the equation v over r. So you do that for both sides. You go ahead and solve for VA, plug in our values that were given, and you end up with the velocity out at position A at the apogee is 2,820 meters per second. So the idea here is, though, that the angular momentum before equals the angular momentum after. Just like when we studied linear momentum before equals linear momentum after.